students, welcome back. This is Taura's Elbow Bump. How are you? Are you doing okay? How's your family? Are they okay? Remember, if you need anything, send me an email and I'm happy to try to help in whatever way I can. So lucky you, you get to hear my voice for another lecture. But the best part is we're going to continue our conversation about the sampling distribution and talk about how to calculate the standard error and when it's appropriate to use the estimate of the standard error. Yay! So just as a quick review, when we talked about the central limit theorem for the sample proportion, we were basically looking to see that if a random sample of n observations, however many observations, is selected from a population, any population, and the sample is large enough and the population is sufficiently large, then the sampling distribution of the sample proportion will be approximately a normal distribution. So we can take samples and take the proportion, take samples, take a proportion, we're going to end up with a normal distribution. We can use the central limit theorem for sample proportions, but certain conditions have to be in place. First, the trials have to be random and independent, and the sample size has to be sufficiently large. We looked at how the successes and the failures need to be greater than 10. We also need to make sure that the population size is large enough. So we need to make sure that the population size is at least 10 times bigger than the sample size. Understanding that we're trying to make an inference about the true population proportion, we need to account for error. And we can account for error by looking at controlling the bias, and we can control for bias by making sure that our trials are random and independent, and we can account for precision by trying to increase the sample size as large as we can, as close as we can get to the population size, and we can control for standard error. We can reduce the standard error. As a quick reminder, here's the example that was presented in our lecture about the central limit theorem. Here is my entire population. We kept it small just so we could talk about it very easily. So in this situation, we have 5 children, and 2 of the 5 children are male. So 40% of the children are male. And if I grabbed my calculator, I could actually prove that to you. So here, right here, I've got 2 out of my 5 children. 2 divided by 5 is 0.4, which is the same as 40%. Okay, this is the truth. Now, what if I can't see the truth? I can only take samples to estimate the truth. Here, I took a random sample of 3 of the people in the population. In this first sample, I ended up getting a boy and 2 girls, which means that 33% of the sample is male. In this instance, I took another 3 kids, right, chosen at random. 2 out of the 3 children were male, so that would be 67%, and I'll show you here. 2 out of 3 are males, so 6.666, which rounds to 0.67, and we can write that as a percent as 67%. And in this last situation, we took a random sample and there were no boys, there were no males, so there was 0 out of 3 were male, so it would be 0% or 0.0. Okay, so there is one true population proportion, which is 40, which was the last slide that we looked at. This is the truth, that 2 out of the 5 are boys, and the true population proportion is 0.4 or 40%. But there's many sample proportions. Here I drew 0.33 or 33%, here I drew 0.67 or 67%, and here I drew 0%. Okay, so there's lots of sample proportions. If I were to start to plot this, the sample proportions themselves would actually start to look like a normal curve. And the mean of the sample proportions would start to become close to the actual true mean. So here is my, if you look at my example here, there were 10 total draws. There was 1 draw where there were 0 boys. There were 6 draws, 1, 2, 3, 4, 5, 6 draws, where there was 1 of the 3 people in the sample were boys, so 33%. And then there were 3 draws where 2 out of the 3 people in the sample were boys, okay? And if I got 1 times the 0%, plus 6 times 33%, plus 3 times the 67%, I would get 3.99999, and if it divided it by 10, I would get 0.399, which is 39%, 39.99%, which is extremely close to the true population mean. So basically what this is happening is the sampling distribution is starting to form a normal distribution, and the average of that is getting me close to the true population proportion. Let's look at an example that you actually might have some experience with in real life. So let's think of a dice, just one die. And a die has 6 sides, right? On one side of the die, you have a 1, like the 1 dot. Another side has a 2. Another side has a 3. Another side has a 4. Another side has a 5. And the last side has a 6. Okay? And if I were to take this one die and roll it, the probability of rolling a 5 would be 1 out of 6. Makes sense, right? So here's all my possibilities. The probability of rolling a 5 would be 1 out of this 6. And I would be able to express that as the probability is 1 out of 6, and that is approximately 0.167. It's like 0.16666, but you can round it to 0.167. Okay, we know this to be true. If you've ever touched a die, rolled a die, you've seen this happen. Okay, so we know what that is. But the thing is that if I roll the die 6 times, I won't necessarily get a 5 one time out of those 6 times. Anything can happen. Things are random. Let's look at a simulation here with some data in StatCrunch. So this is a simulation, and it's going to keep track of what I roll every time I roll one die with 6 sides. So here I'm going to go ahead and roll it once, and I got a 3, and it's going ahead and going to kind of make a little table for me. Okay, so if I roll this thing 6 times, I will expect to have gotten a 5 at least once. So that was 1 time. Now I'm going to run it 5 more times. 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5, 6 rolls. I have 0 5s. Why is that? Well, because things happen, because it's random. I'm not guaranteed to roll a 5 if I roll a die 5 times. That's just the probability of it. Let's see what happens now. Let's try to run it another 6 times. Close and run it 5 more times. Aha! Okay, so this time I got a 5, and although I'm expecting the proportion to be 0.167, right now the proportion of my rolling a 5 has only been 0.0833. What happens if I run this? Let's run this 30 times. So 5, 10, So notice here I've run it 30 times, and this time the proportion is 0.1. So it's telling me that I have received a 5 10% of the time. Again, it's wrong because I'm expecting 16% of the time. Why is the discrepancy? Because things are random. Okay. Now, if I did this enough, look at my proportion number right in through here. Okay. let's say I ran it 1,000 times, look what's going to happen to my proportion. Whoa. It went all the way up to 0.544. Let's run it another 1,000 times. Look at that. 0.1635. Let's run it another 1,000 times. 0.1617. Let's run it another 1,000 times. 0.1658. Let's run it another 1,000 times. 0.167. See how it's getting closer and closer and closer to the expected proportion? It's because I'm having these huge amount of runs. It took me 5,030 times to actually get to the proportion. Okay? If I would have just gone with the original 6 rolls, right, instead of the 5,000, there would have been some degree of error in that. So here I have a 6-sided die that I've gone ahead and thrown 60 times, and I've recorded the number of times a 5 was rolled. If I notice, it's not going to be exactly 0.167. It's going to be close. In fact, and if I missed any 5s, I'm sorry, but I went through this really, really carefully 3 times, looking for all the 5s. I hope I highlighted them all. If I rolled it 60 times, I would be expecting to get at least 10 5s. I didn't, because things are random, right? So I got close to it. I got 8 out of 60, 13.3% instead of the 16.7% that was expected. Okay, so this is one of my samples ended up being 13.3%. Here I did this 5 more times. Here I did another trial of 60 rolls each. This time I got another 8 out of 60, so I got 13.3% again. Here I did another 60 rolls and I got 7 out of 60, so it was 11.6%. Here, same thing happened, 7 out of 60, 11.6%. Here, I got 6 out of 60, much lower than the other ones, 10%. And here, I got 16 out of 60, much higher than I'm used to getting, 26.7%. Okay, but ultimately, all these sampling, if I were to keep doing this over and over again, these proportions would be creating a normal distribution. When we talked about standard deviation, we talked about how data is different. Standard deviation is a measure of variability. Measures of variability describe how the data is different. Here is my true population proportion. For a set of dice, rolling a 5 on a 6-sided dice, the probability is 1 out of 6, or approximately 0.167, or 16.7%. Okay, this is a weird number line. That would be right about here. Okay? The difference between the results of the samples and the true population proportion is called the standard error. So that spread, that difference, okay, how much the samples differ from the true population proportion can be described as a standard error. So it's the standard deviation for the samples from the true population proportion. In order for this to be in place, you have to have a normal distribution. Therefore, you must apply the conditions of the central limit theorem, or you have to check to see if the conditions of the central limit theorem can be met. As a reminder, in order for the central limit theorem to be applicable, the trials must be random and independent. The sample size needs to be sufficiently large, and the population size must be sufficiently large. If that's true, then we can say that the sampling distribution is approximately normal. Now, sometimes you might get lucky and they might just tell you that the distribution is normal. The way that they would signify that to you, they would tell you, is they would give you this n right here. See this n? This n, when it's outside of the parenthesis, is telling you that you have a normal distribution. It's not saying that it's a population size. It's saying that you have a normal distribution. Within the parenthesis, you're going to have the true population proportion, a comma, and then the standard error. This is the formula for the standard error. P signifies the true proportion of the population, and to calculate the standard error, you're going to take the proportion of the population and then multiply that by a whole minus the proportion of the population, and you're going to divide that by your sample size. So as you can see, the sample size being in the denominator, if you have a small sample size, then you're going to have this fraction is actually going to be a larger number than if you, or a larger value than if this n would have been a big number, and then this value would have been a very small quantity, a very small value. So that's why this sample size is so incredibly important. The larger the sample size, the less error you're going to have. And then you're going to take the square root of that. Let's calculate the standard error for our dice example. So here's my dice example. If you recall, we talked about the probability of rolling a 5 is 1 out of 6. This is known. There is no question about that. This is the true population proportion. We rolled 60 times on 5 different trials. So our sample size is 300. 300 dice were rolled here in my example. I'm going to go ahead and write my standard error formula over here off to the side. So I've got standard error equals the square root of the proportion times a whole minus the proportion divided by my sample size. So it looks like I have the proportion, it's right here. I have my sample size, it's right here, and really the only other number I need is 1 whole minus 1/6. So if I can think of 1 minus p being the same as 1 minus 1/6, and 1 whole as being 6/6 minus 1/6, right? Then I'm going to get 5/6 as this 1 minus p. And if I bring over my handy dandy calculator over here, I've got my Google calculator that I'm going to go ahead and use. And I do 5 divided by 6, I get that this is my 1 minus p. All right, so let's use Google Calculator to go ahead and write all this in here. So I've got this here, SE equals the square root of 1 over 6. Now, why am I leaving it like this? Because remember, this is rounded and we're trying to be precise. So I'm going to go ahead and just leave it as the fraction. Times 1 minus 1 over 6 divided by 300. All right, and let me go ahead and put that into my calculator now. So here's my calculator. I'm going to go ahead and clear everything out. And I'm going to get 1 divided by 6 equals, okay, so I'm not going to round this, because remember, when you round, you lose precision, you gain error. Now I'm going to multiply this times, go ahead and use my parentheses, 1 minus this answer right here, answer. Okay, so see how this is answer equals 0.1 and then tons of 6s? Since this is what they're considering my answer, I can go ahead and just type in answer, use the answer key, and it doesn't, does everything perfect for me. I don't make any mistakes by actually entering it incorrectly. What happens next? Now I'm going to go ahead and divide by 300. Divide by 300 equals, I get this number, and now I can take the square root of my answer, and I get that my standard error is 0.0215. Perfect. That's it. So my true population proportion is 0.167, and the standard error, the standard deviation of the distribution of my samples around the true population mean for a sample size of 300 is 0.0215. Instead of saying that the standard deviation of the sampling proportions are around the true population proportion, you can say that that number is the standard error around the true population proportion for a sample size of 300. Now, the purpose of taking a sample sometimes can be to estimate the population proportion when the true population proportion is unknown. If the true population proportion is unknown, then the standard error can't be calculated. However, you can use the sample proportion, what we refer to as p-hat, as an estimate for the true population proportion. And this calculation will give you an estimate of the standard error. So it's not the true standard error, but it's an estimate of the standard error. Let's look at an example when we just have information from our own personal sample. We don't have the true population proportion. Okay, so it says 200 randomly and independently selected American drivers were asked if they text while driving. 48 of them admitted that they did. So the question does not have any information whether this is a normal distribution or not. So we need to check to see if the conditions of the Central Limit Theorem can be met so that we can assume normality. So in the question itself, it states that the drivers were randomly and independently selected. So check, that's there. 48 of them admitted that they did text. So the successes is 48, that's greater or equal to 10. And if 48 of them admitted that they text, and there's 200 total, that means that 152 did not admit to texting, and 152 is greater than or equal to 10, so that meets the condition of large sample size. Finally, the population size is the number of American drivers. That's a huge number. That's certainly more than 10 times 200, which is 2,000. So all three conditions of the Central Limit Theorem are met. So the conclusion is that the distribution is approximately normal. Okay? So according to our sample, 48 out of the 200 said that they did text. Okay, so I've gone ahead and posted this question into Ziteboard. And I'm going to go ahead and do my calculations here. So it says that 48 of them out of the 200 said that they did text. Okay, so 48. So my p-hat, because this is my sample, is 48 divided by 200. And if I drag my calculator over here real quick, where's my calculator? Boop. I've got 48, and I'll clear it and do it again. 48 divided by 200 gives me 0.24. So I'm going to go ahead and write 0.24 here. 0.24. Excellent. Now I want to find the estimate of my standard error. I can't calculate my real standard error because I don't have the true population proportion. I only have the sample proportion. So I'm going to use standard error equals the square root of p-hat times 1 whole minus p-hat divided by n. All right. So p-hat is going to be 0.24. And then I'm going to multiply that by 1 minus 0.24. And I'm going to divide it by my sample size, which was 200. And I guess good practice would be for me to write my sample size up here. Wonderful. So now I'm going to go ahead and put this into my calculator very carefully. Clear this out. And I've got 0.24 times parenthesis 1 minus 0.24 equals. Now I've got the numerator divided by the denominator, which is 200. And now I'm going to take the square root, which I can do by hitting the square root key and just telling it to put the last answer that I calculated in by hitting the answer key, equals, and I get that the estimate of standard error is 0.030. Why is this an estimate of the standard error? It's an estimate of the standard error because I did not have the true population proportion to work with. I only had the proportion of my sample. So I used the sample proportion in order to figure out the estimate of the standard error. The formula is exactly the same, and I probably should put this here, estimate of the standard error. It's the exact same thing, except for the estimate of the standard error, you're using p-hat, which is your sample proportion, and for the real standard error, you're using the true population proportion. All these measures sound a lot alike, and they are similar in the way that they describe differences. They describe the spread of a distribution. Definitions of each. A standard deviation is the degree to which each individual piece of data differs within a single sample from that sample's mean. The standard error is the standard deviation, or the differences, of all samples collected from the true population proportion. And the estimate of the standard error is the standard deviation, or the differences, of the samples collected if you have a sample yourself. So what's the big idea? Well, first, if you have a simple random sample of a certain size and the true population is known, you can model the distribution of the sample proportions with that has P as the true population proportion and the standard error formula. The same can happen with the sample proportions if the true population proportion is unknown. In that case, you will use your sample proportion in order to calculate the estimation of the standard error. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there is a new video for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!